Good evening. My name is Brian Gaumer, and I am going to go over the Messler Chapter 10 on scaling. Messler's definition for scaling out of his book is scaling is a linear transformation that enlarges or increases or shrinks and diminishes an object by a scaled factor that is the same in all directions. That would mean his x, y, and z axis would be the same proportionally as you would go larger or smaller. This, in simpler terms, the way I wanted to talk about it is it's projecting an object either smaller or larger where all the measurements are changed by the same number. So, for instance, if I wanted to do something and double it in size where I would go 2 to 1, all right, every distance would be doubled. My length, my width, and my depth would all be doubled, and that would be a scale of 2 to 1. It would be twice as big in all three of the major directions. There are some various applications of mathematics, obviously, that go into scaling. So, an object can be scaled larger or smaller than its original base size for the intended use of the projection. Now, the projection would be whatever we're trying to accomplish from this. We can do it in testing of prototypes, we can do it in scaled models. When we look at scaling, it's based off the ratio of two numbers, the actual measurement compared to a larger or smaller rendering, which we would like to have the end result be of our projection. So, for instance, if we have a larger object, okay, that larger object would be signified by a 1, and then it would followed by however the smaller object where we're going to render it in that scaled smaller version. So it would be divided by a number. For example, if I have HO model trains here, and HO model trains are almost identical replicas of real life trains, the scaled model of an HO train is 1 to 87. So that ratio means for every 87 feet of actual train, the model train would be scaled down to about 1 foot. Now, in real life, with an HO train, the most average cars are about 6 to 7 inches in length. So you can see where you would take a very large train that could possibly be over 50 feet, and now it would be scaled down pretty small. The other example of scaling is obviously if we go from a large object to a smaller object, and now we have something maybe that is so small that now we want to scale up to be seen by the human eye. One that I've seen in the high school is with our biology teachers. They have a lot of stuff with cell modeling, looking at small, minute, or microscopic cells, and have large teaching aids that they could use for their classes. So, looking at like a biology scale model of a cell, you're looking at somewhere roughly a ratio of about 25,400 to 1, which would mean about every 1 foot is actually represented by 25,400. So you would see where this is a very, very large magnification. You've scaled up that very small actual model. So scaling in the real world, a lot of times engineers are going to use prototypes. They're going to use scaling and prototyping because obviously when they're going to do their testing or when they're going to do any type of presentation, they're probably not going to have the material or the wherewithal to waste enough time to make the whole part. It's more financially responsible to have smaller scaled models. It allows you to kind of do the exact same test you would on a lifelike model, but these smaller scaled models, or sometimes in the case of larger scaled models, will allow you to see how the object will react in real life versus if they don't have to test it on something that would be a manufactured product. So looking at civil engineers, we look at models where civil engineers create. Maybe they're going to do some wind testing or shear testing for buildings, bridges. They can put these sort of models through many different tests that would allow them to, kind of predict how the outcome of these designs would work, in the fact that they're not having to actually build the real building, or they're not going to actually have to build the full-size bridge. Architects would also use site models, possibly to look at the overall design of their architecture as far as their site plans. So how their course house would lay out versus maybe the landscaping and the driveway versus the trees, maybe the element of where the sun sets and where sun rises and sets. So all those things will allow an architect to have an idea, again, kind of look at their proof before they go and actually build the existing building. So architects, again, use these models to formulate will their designs work and the flow of their designs throughout their product. One other process of scaling that actually I learned about in this chapter is variant scaling. I didn't really have never encountered this when I did anything with variant scaling, but what it's telling me is that one of the dimensions of the object is not scale proportional to the other two. So, for instance, the example that they used were stretch limousines, that there are some definite consistencies for maybe height and width, but then the length is now scaled out of proportion to the other two, which then would give you the image you see here with a scale limousine. Not as common, like I said, that's why I've never even really used it, but I could see where the applications could be used by different engineers. Some of the ways that I use scaling in my class, this is in a version of what they call the T9 Automobile Block with my 9th grade engineering students in Introduction to Engineering to Design. Students are given a scaled model, which is pretty lifelike of a car, and they have to then create these drawings in Inventor off of this part. So now these drawings, they're going to have every different dimension for every part of this car. And when they go to draw them and create them in the 3D modeling program, they'll have to then present them as part of different scaled versions. So what I have them do then is calculate from the scaled model, what is the actual, model of a wheel for an actual vehicle? What would your overall dimensions be? And I have them just go through the procedure of trying to then make this car lifelike so they can use it, and it's not just then a toy. So we use this part as both a teaching tool to use our 3D modeling software, but then also a scaling application as well. Here's another scaling application that we would use in our 11th grade civil engineering and architecture. Obviously, we want students to learn a little bit about truss work and a little bit about stressors and bridges. So we have students solve a problem that we tell them you have a ravine of 150 feet, and we need you to scale do a scaled version of the bridge that would span across those two areas, or those two lengths, or that length. So now what the students do is, in a smaller scaled version, they take it down to 1 to 15, so it's 1 to 15, and they would build a bridge. It's obviously going to be no longer than 15 inches. So when they do this now, they're also taking into account each of the truss works and the spacing of the truss work, how it would be spaced over a 150-foot span, but now they've shrunk it down to, basically every 10 foot is an inch. The last example that I have right now for you is our architectural model. This is actually done in 2 of our classes. It's done in our civil engineering and architecture class, but it's also done with our Technology Student Association, which is our student club, as far as a regional and state competition, where we have a competition that this is entered in called Architecture Model. And now what the Architecture Model is will give the students some sort of parameters of what the problem is, and then they will have to design the site layout to be able to account for all the things that they want encompassed in their design. So you can see here where there is, shrubberies, fences, trees, a pool, the garage. All that stuff has to be proportionally laid out so that it fits on their plot plan of their design. So again, that is scaling In closing, thank you very much.